Can you hear me?
I know.
Yep.
Much better.
Yep. All right. Well, it's 3 past the hour, so I'd say we go ahead and get started with the introduction, guys. My name is Matt Bracey. I'm president of the New England chapter of IMAPS. I want to thank everybody for joining us this afternoon. We appreciate it. Today's session is our second virtual symposium session. It's the RF microwave session. Our general chairs for the technical symposium are Michael Johnson and Dave Soms. They're on the line today hosting this, as well as our session chairs, Tom Terlizzi and Chandra Gupta. Let's see. Like I said, I'm Matt Bracey. I work for myself. I'm a manufacturer's representative of MSG Sales. I cover New England for the most part, and I've been doing this IMAPS things for about 6 years for the New England chapter, and I've been president since July. So it's been a fun year to take on the presidency, and we're working at it. We're going to keep going. Just so we go ahead, Dave, to the next slide, I think. Yeah. All right. So to talk a little bit about the New England chapter and IMAPS in general, it's an international organization that is an International Microelectronics Assembly and Packaging Society. We are the New England chapter, so we cover the 6 New England states. We're the largest and most active chapter in the organization. And we generally do a in-person technical symposium and trade show in Boxborough, Massachusetts in the springtime every year. This would have been our 47th year of doing that, and it's the first year we haven't done it. So in order to continue on our tradition, we've decided to go virtual, and this is what we're doing. So we're doing every other month we will be doing a symposium session, and then the opposite months we'll be doing a technical meeting in the evening, just to try to give back to our community and keep everybody active. And we appreciate all the help and all the support. And I should also mention this is an all volunteer organization, so all the work that goes into us, and there's quite a bit of it, is done out of the goodness of our own hearts, really. And I know Michael and Dave could probably testify to the amount of work that goes into getting this to work. So with that said, I'm going to pass over the microphone to Dave.
Thanks very much, Matt. Welcome, everybody. My name is Dave Soms. Michael and I are the co-chairs for the symposium this year. Yes, it's a fair amount of work, and what's surprising is it's actually more work to set up these virtual sessions than it is to set up the in-person sessions. It's quite puzzling to find that out the hard way. I've worked in electronics thermal management for 42 years. I resigned from a full-time position 18 years ago to start my own consulting business. It's a one-person consulting business, and my focus is helping companies to grow new businesses in the area of thermal management for electronics, and that covers a pretty wide range. Michael Johnson is Senior Principal Manufacturing Engineer for Maycom Technology Solutions in Lowell. Michael has been with the company for 21 years. He's a graduate BS Mechanical Engineering from Worcester Polytechnic Institute in Worcester, a university that we all know and that has been very active in participating with IMAPS New England. This is now our third virtual meeting schedule. As Matt explained, we're alternating from one month to the next between the technical sessions that we've taken out of the original 2020 symposium and the normal monthly chapter technical meetings. So September 22, we had our first virtual symposium session that was chaired by Lee Levine, and that topic was interconnects. October 27, we had an excellent presentation as a chapter technical meeting given by Eric Perfecto from IBM Research, lifelong IBM employee, on heterogeneous integration and artificial intelligence, the relationship to packaging and how it impacts packaging. The chair for our chapter technical meetings is Richard Holman, and I believe Richard is on the call today also. Today we have our second virtual symposium session titled as Session B, and it is a microwave, RF and microwave topic. Tom Terlizzi from TJ Green Associates will be the chair. Chandra Gupta is also on. from CPI in Beverly. He is the co-chair for the session today. We have 4 what we think are excellent technical presentations, and we will introduce the speakers. We have some logistics comments. For questions, if you have questions as you listen to the individual speaker, if you go to the bottom of your screen with your pointer, that will pull up in Zoom, which is what we're using here. That will pull up a taskbar at the bottom, and you will see a little balloon for chat. If you tap on that, that will open up the chat box on the side of the screen, and you can type into that what your questions are. My suggestion would be select everyone for who the question is going to go to. Michael Johnson will shepherd the questions as they come in, organize them, and then manage or moderate the Q&A session. This has worked very well in the past. We anticipate that it will work very well today. Please do keep the questions fairly short so that it is possible to fit them into the chat box and have Michael read them out for the speaker. Then the speaker will respond. We expect at a later date that you will receive an email from the chapter that will give you information about the availability of the presenters' slide sets for those that we have permission to publish. We're expecting this will go till about 3:35 p.m. this afternoon, once we finish the last presentation, Q&A, and final comments. We would like to ask you, Matt, if you have the ability to shut off everyone's microphones except the speaker, that would be great. But otherwise, you can turn off your microphone individually, again, using the chat bar. If you bring your pointer down to the bottom of the screen, that will pop up the, sorry, not the chat bar, the taskbar. You'll find an ability to shut off your microphone. If you are working from home and you have small children or you have a dog, it's often helpful to keep your microphone on mute. I'm laughing because we've had, I'm sure you've all seen this in other sessions where someone's dog barks and so on. Anyway, to get started, our RF and microwave session chair and co-chair are shown here. Tom Terlizzi is Associate Consultant with TJ Green Associates, also Vice President of GM Systems. And you can see a fairly considerable biography here. Tom has been working for more than 40 years in the microelectronics industry and doing packaging for aerospace, telecom, commercial systems at several different companies, including Aeroflex on Long Island, Norden Systems, which became part of United Technologies, what was Grumman Aerospace, today Northrop Grumman, and General Instrument Corporation. He has a BS degree in electrical engineering from the City College of New York, MS in electrical engineering from NYU Polytech. He's published articles, given tutorials, edited books on electronics packaging, consulted for the Department of Defense on packaging, is a past president of the IMAPS Metropolitan Chapter. With TJ Green Associates, Tom is the exhibits chair in the program and a program committee member. If you're not familiar, Tom Green runs an annual conference, CMSE, Military and Space Electronics, that's normally held in the LA area, but of course is virtual this year and will be virtual next year also. I've included Tom's email address here if you wish. Chandra Gupta is also with us. He is the session co-chair, has a PhD in electrical engineering and MBA degrees, 30 years of experience plus in RF and microwave, developing, managing, producing a wide range of assemblies and components. He's held positions from Vice President of Operations and Engineering at Hurley Industries to General Manager at Aeroflex, Director at Hittite Microwave, and has served as a RF and microwave consultant. He's working today with Communications and Power Industries, CPI or CPII in Beverly, Massachusetts, and he's a senior member of the IEEE. I will now stop screen sharing and turn over the screen to Tom. Tom will introduce the first speaker. So you should be able to now see the screen, I hope, Tom, and you should be able to take control.
Okay. First,
if all works well, that is.
First presentation is for by Jay. It's called Organic Packaging for 5G and 40 gigahertz applications.
Tom, I'm sorry, but audio again?
All right, got this all the way up. Yeah,
Better.
he's the co-founder and GM president of Agile Microwave Technology Inc., a fabulous manufacturer of microwave amplifiers and microwave modules. He has a BSEE from City College in New York, an MBA from California Coast University. He founded High Tech Computers in 1985, and he co-founded Amplicom in 2000, which was later acquired by Aeroflex, which is now Cobham, where Jay was the director of RF and microwave products. Okay, Jay?
Yes.
Tom, you need to relinquish screen sharing.
I do that? Okay.
He should be good. Jay's on.
Yeah, I'm on. Thank you, Tom, for that nice introduction. What I'm going to talk about today is 5G and the millimeter wave organic packaging. This is one of the issues in millimeter waves that needs to be solved for 5G to be implemented fully. And so we think it's an important topic, and that's what I'm going to talk about. Let's see. Okay, so today's topics that I'll be covering is just very introductory level of what 5G is, what is the organic package as opposed to other packaging, what is QFN, and, what is air cavity as opposed to encapsulation or other partial cavities, and what are the advantages of it. And then we actually picked a commercially available quick pack package, which I'll talk about, and how we measured and implemented a board design to work up to 40 gigahertz or beyond. It actually works to 50 gigahertz, but so those are the topics that I'll be covering. So going on talking about everything is being driven pretty much on the commercial side by 5G right now. And so as it states, 5G is basically 5th generation of mobile network. And its wireless standard is the next standard after 4G. So it's 3G and 4G, what's implemented mostly right now. There are a lot of advantages to using the 5G as opposed to 4G, mainly bandwidth and low latency. And I'll come back to that a little bit later. But the amount of data basically is, in simple terms, the amount of data that you could transmit and receive, and how quickly you could do it is the main advantage of 5G. And everyone's heard the commercial of T-Mobile and AT&T and Verizon. They're pretty much implementing the 1 to 6 gigahertz of the 5G version right now, but they're all in the works, and they have some setups in the urban areas that are working at millimeter waves. And the 5G frequency range basically that everyone around the world is working on, it's from 24 gigahertz all the way up to 43 gigahertz, in that range. Narrower bands, but different companies, different ranges. One of the features of the 5G network is the low latency aspect that is required if we're going to have if we're going to implement driverless cars, and that's the main driver for that part of it, as well as the higher speed allows, a whole bunch of applications that were not possible before. So as I mentioned, we're going to talk about organic packaging. So what is organic packaging as opposed to other materials? So when we talk about organic packaging, we're talking about, plastic type of material, encapsulant materials, and as opposed to a ceramic or metal, as you see on the bottom. This is some of the pictures of the ceramic packaging and metal packaging you see in amplifiers and other things implemented. And there are two types of primary within organic. There are two types of way of doing it. One you see on the left side is the completely encapsulated, where you basically have a dye in the package and then some organic material that's put on the top and cured so that it becomes the thing. And the other option is to have an air between your dye and the cover or the lid. And those are the air cavity packages. There's some advantages and disadvantages to each one, which we'll talk about. So basically, within the packaging, then you have different methods of interconnect to the next level, which would be a board, because these are SMT components. So the processors and all the electronics that are not millimeter waves or RF and microwave, they tend to use the leads, what you see the picture on the left side, which are basically they're called J leads, or they're pins that are coming out of the package, and then you solder those onto it. The disadvantage of that is that for high frequency, it doesn't work very well because of that transition. It's going to not be a good 50 ohm match, as well as it's going to pick up other interference and things that it will limit. That shape will limit the frequency that you could go. Majority of the time, that frequency limitation is around 6 gigahertz. So if you're below that, you may be able to get away with it with a little higher loss. But a better packaging for RF and microwave is what's called QFN, which is basically quad flat pack, no leads. And these packages have an advantage, is that basically the transition is directly metal. So you don't have other shapes or transition. It goes right down. So it's the shortest distance. So you have the least impedance for high frequency, and that's important. So a lot of these packages are getting popular, and they're becoming standard in the industry. And they do have organic package, what you see on the pictures right now, and then their ceramic package, but I'm going to primarily focus on organic packaging today. And so, as I mentioned, we partner with Quick Pack QFN because they have nice packages and they're readily available commercially. You could go to their website and order these, and they have them in stock. And they come in a whole bunch of different formats. We selected the 4 millimeter package because we're going to use to prove our feasibility of working to millimeter waves to 45 and 50 gigahertz. We selected commercially available amplifier MMIC from OMIMIC, and so we matched the package to it. That's why we selected 44 millimeter package. When I show you the assembly, you'll see why it fits the best. But the critical application here is that you have to pick a package that is close to your die, so you don't have long wire bonds or ribbon bonds, and that will add a lot of inductance to your design and also radiate more. So you want to limit the length of your wire bonds and ribbons. So basically, this is an air cavity package. It has a standard JEDIC standard footprint on the bottom. So that's a good thing about it. You could find a lot of information about it using those standard packages. And then it has an organic lid, which you could buy it with a B-stage epoxy already on it, and then attach it that way. And also, if you notice, this package has a different pad length and pitch. So basically, it's about 0.5 millimeter spacing between the traces, and 0.23 millimeters of the actual pad size. But that you could get different sizes depending on your board traces. Depending on what board you're laying out, you could select a different package. So let's go. This is a little more detail on the basic layout or the design of the package. We would mount our, in this case, it's a MMIC amplifier, but our die on the center of the package, which is just basically used also as a heat sink. It's a direct copper material, so it's a very good heat sink, and it's very small. It's about 20 mils, so it can get the heat out very quickly, and it's thin. And the main advantage of using an air cavity package is that majority of the RF and microwave, mimics and switch die, any die you tend to use, they're designed for air cavity or air as a dielectric. And if you were to put some other encapsulation or other material on it, that changes its entire characteristic. And you would almost have to have the die designed for that. Otherwise, you're going to get a different type of performance. You're going to get a lot more losses, and it's not going to work as designed. So that's the reason for the air cavity. And the other thing that's of key important in the package also is that since it's organic material, the lid is kind of like plastic, so it's non-metallic, because with a lot of gain in particular for amplifiers with a lot of gain, if we have a metal lid, it will have some resonant frequencies, and it can create all kinds of bouncing off the wall into the cavity, and you can have all kinds of waveguide moding. So the plastic works well that way. It doesn't, it has the least amount of reflections back and forth. So that's the reason we picked the organic package, and it works better. I just put some, just to give you an idea of at 40 gigahertz, your frequency wavelengths you're dealing with are really, really small. So every cavity, every length of your wire bond will have an effect on your performance. In particularly, if the longer it is, you're going to have more losses and more mismatches. So this is just to demonstrate it. We went out and tried to pick the most broadband MMIC we can pick, and this is basically O-MMIC's fiber optic amplifier MMIC that works from DC or kilohertz to 54 gigahertz. And it was designed for the fiber optic modulator driver application, and it's a distributed, if you look at the picture on the thing, it's basically a distributed amplifier design with multiple stages. And this is right from their data sheet. They do require that 100, if you see that C1 on the drawing, they do require 47 picofarad capacitor placed fairly close to your VDD. And if you place it too far away, it's going to cause other signals to get into your RF. So that's why I'm telling you that, so that we also place this capacitor in the package. So besides the MMIC, we have this single layer capacitor in there also. And okay, so this is the basic layout or the diagram of the MMIC in the quick pack package that we did. So this is basically what per the data sheet is showing you the 47 picofarad capacitor. That's where we get our 5-volt bias from, and the input and output, RF input and RF output. And if you notice, this MMIC fits very well into this 4mm package because we have the least, the shortest ribbon bonds. And what we did is we selected to use the 3mm ribbon bond to get a better, lower impedance, a better impedance match and lower inductance. So that's what the 3mm ribbon. You could use multiple wire bonds. That would work also, but this works. So this was the layout. And this is the actual photo of the die in the package. So if you could imagine the way QuickPack makes this package is they have this copper, which is gold-plated frame, and then they add the plastic encapsulated material. So it's a very simple design, but that works well for high frequency. And I'll show you on the next slide the board. So this is basically a package mounted on the Rogers board without the lid. And so the key, one of the keys to selecting using a millimeter wave, surface mount packages like QFN is that if you look in the industry, Kyocera's had packages that work up to 65 gigahertz for a long time. But the challenge is not just what they do is they give you parameters for that package. And yes, the packages will work up to very high frequency. The challenge is really, how do you mount that package on a board for your next level assembly and still maintain the frequency performance? And what we did is, in this case, what we did is you see those grounding via pattern on so we use the Rogers it's a 4300 series board. I think I'll tell you exactly on the next slide, but these ground patterns are not random. They were simulated, and the VSIs, they're simulated. So it's and we provide this to the customer that they would have to copy our pattern or use the same pattern, because those patterns are very important for ground transition from the package to your transmission lines on the board. They have to be matched. The more mismatches you have, more it's gonna radiate on your board, and more losses you're gonna have at higher frequencies. So it's very crucial that pattern may be maintained. But that's how it's designed. So it's kind of designed like ground signal ground. That's why you see the vias on both sides of the signal. And then this is the board picture you see on it. And basically, when we manufactured the board to take out the losses for the line, we did at the same time, you see on the bottom, that's made as just basically a calibration substrate. So The old MMIC die requires 2 DC blocking capacitor. That's what, it's hard to see it, but they're on the RF line. You could see the 2 capacitors. So those capacitors are mounting on the calibration line, and that this way we can calibrate out the losses of the line. This way we know our true performance of the package. And then we use the Southwest 2.92 millimeter connectors that work up to, they have pretty good performance up to 43 gigahertz. And again, so this explains to you what it is. Actually, here I point out the DC blocking caps with the arrows. You can see that, and the chip outside is just a 5-volt regulator, so we can have a long line in the lab from our power supply and not worry about stuff getting into the unit. And this is just basically the QFN package mounted with the lid on it and the calibration substrate. And so we did this for this die and the package, and we took S parameters from 10 megahertz to 40 gigahertz. This is the actual capture of the screen of the VNA. So you could see the actual performance of the die. And if you look on the S21 screen, which is the bottom left, it shows you the loss of the through line. So that's just the board loss of the line over frequency. And the top one, it shows you if we calibrate that out, what our performance of our MMIC is. And if you look at the MMICs, which we have the part number, if you look at the MMICs part, where the performance is pretty close to the data sheet. So this shows that our mounting our die in the package and mounting the package on the board, we have very little loss, and our matching is good all the way up to 40 gigahertz. And on the right side is the S12, which is the isolation, and that looks good also as expected. So this basically, we took a commercially available package. We took a commercially available, die broadband distributed amplifier. We put it in the package, and then did the measurements to prove that the design and implementation works. And here I have some links that for packaging or information on it. And I think that's it. Turn it over back to you guys.
Thank you, Jay. Great presentation. Just checking the chat box, just a reminder to everyone, if you have any questions, please submit them through the chat box. We did have, for the first one that came through, is there a general rule of thumb that is used for the thermal limit in watts for a given air cavity package relative to package size?
Well, the rule of thumb is basically 45-degree heat spread, Excel. That's what we use. But since the package is it's copper, it's a solid copper, and it's only 20 mils thick. All of our thermal calculation, it wasn't the package. It's really the next level assembly that drives the thermal limitations. So the question is, how fast can you get the heat out of the board with the vias and what your attach method, what kind of voiding are you going to get? So with the solder, we found normally you're not going to get better than 90% coverage. So that means you're still going to have 10% voiding. So we thought that the package thermal was negligible compared to the actual assembly afterwards.
Okay.
Yeah.
I guess one more question, that I have is, did you see any other assembly challenges or or performance-related challenges that you didn't envision originally using the package, or did everything kind of line up?
Yes, the key is finding the right size package for your die. That seems to be the key, and what you need to put in there. So if it's a multi die in a package, then you could probably manage it. It's easier. But if it's a single die, there's not much you could do. You're gonna have to either have long wire bonds or put in an additional line length to get there. So the challenge is finding the right package for your die. And as you notice on this package, we also have the input of the RF and the output of the RF doesn't align. So that's always a challenge, because then you don't have a straight line. So you'll have to, that's why selecting a package is also more important. And the other challenge is the assembly challenges, of course, there. As these QFN has gotten smaller and smaller, it's very hard to get a consistently to put down these packages consistently well without voiding. The solder, basically the solder is, so the process is going to be the most important thing, because any breaks in the ground under the package is going to cause resonance in your performance. So those are the challenges. Yeah.
Thank you. I don't see any other questions coming through on the chat box right now. Guess we can pass it. Thank you, Jay, again, for the great presentation. And I think we'll pass it back to you, Tom, for the next introduction.
Okay. All right. The next speaker is Daniel West, and the title of his presentation is High Temperature Passive Component Update, Transient Voltage Circuit Devices. Daniel graduated in 2010 from Mercer University with a BSCE. He's currently a field applications engineer in the technical sales group at AVX headquarters in Fountain Inn, South Carolina. This role centers on projects ranging from simulation models for passive components to product support, new product identification, and applied development. Prior to that, Daniel was a team leader in the U.S. Army 82nd Airborne Division 1-504 PIR, preparing for and performing combat operations during Operation Enduring Freedom. And we thank you for your service there, Daniel. So.
Yes, of course. Thank you for the nice introduction. I'm going to start working on sharing my screen. If I could just get some quick feedback on it.
Yeah, looking good.
Okay, thank you.
Looks good.
Again, thank you. My name is Daniel West. I've been an FAE at AVX for 5 years. The last 3 years, I've been working under Ron Demko, AVX fellow, who also has a presentation after mine. So thank you double to the IMAPS New England chapter for allowing us to speak on 2 different technologies today. And what I want to speak on is multi-layer organic passive electronic components, and why they're an alternate to some current RF products. I hope multi-layer organic or MLO components are unfamiliar to you, because I'll go into an introductory level of what it is, how they're made, why it's made, unique modifications we can do because of the inherent packaging, and finally make comparisons to existing technology, namely LTCC, low temperature coal-fired ceramics. I'm trying to remember to explain all the acronyms. And what you're going to notice right off the bat, in the image on the screen there is the stark visual differences there. And this to me presents an opportunity to look at an introductory level into MLO technology, and I hope you find this worthwhile. Simply put, these are just passive electronic components. These can be surface mount, wire bondable, LGA, land grid array, or castellated packages. You'll notice a familiar surface mount MLCC chip-like appearance on the capacitors and inductors. And while the other devices look very different, they have that familiar PCB appearance. And for the filters, couplers, diplexers. So you may be wondering, how are these related? Well, we start with a extremely low loss organic polymer material, and that can be designed to have high or low dielectric K values. These are repeatable, consistently processed. Discrete capacitors and inductors can be made. It should be, that's easy enough. But by combining tight tolerance, raw material processing, thin film manufacturing, laser direct imaging, we are able to create complex devices. Notice the numerous IO terminations on the filters. These are in very small footprints, low profiles with some added thermal and electrical benefits that I'll get into. The organic polymers are characterized to 100 gigahertz. Again, they come in a variety of K values, inherently low loss. And a friendly reminder that miniature devices, that is capacitors and inductors, are naturally low loss by geometry. Just simply the magnitude of the parasitics are considerably less. If we combine this with the ability to integrate multiple elements, the capacitive and the inductive elements, with micromachining, stacking, and advanced process techniques, accurate simulation, accurate models of the materials, these make for high Q RF devices. I've added labels to the image of a filter that I've shown you 2 other times, but you'll notice that it's just simply a top and bottom view of one device. If we were to view the cross section along the length of the filter, we'd be able to see the capacitive and inductive elements there. The dielectric layers in between, and then the hidden vias depicted again in the zoomed in X-ray image. And then I hope you can see some of the labels, but in the graphic, the illustration, you'll see some of the materials we're using, the weight of the copper, the ½ ounce, and then the high performance substrates we're using. Construction. One of the advantages in construction is we start out on very, very large wafer starts. An 18 by 24 inch, for example, can produce 180,000 parts of EIA 0402. That's 1 millimeter by ½ a millimeter. Dissipation factors on the order of 0.2% at 10 gigahertz, using thick traces of copper, again contributing to high Q. And then we are using the high conductive NPIG, electroless nickel, electroless palladium, immersion gold is used on LGA external terminations that we can also laser direct image, and should pose no problem when it comes to terminating. And then I just added another graphic with the cross section, an illustration of the cross section with labels this time to make it easier to distinguish those materials, and then the kind of orientation of the capacitive and then the inductive elements there. So what we're going to look at here is we covered materials, so now we're going to go into design a little bit. I decided to speak on a complex filter. It's broken down into a few simple steps just to save on time. Of course, there's going to be nuances, and it's going to be a little bit more complex on each step. But we'll get the initial specifications from the customer. Do they want a low, high, or a bandpass filter? And then our simulation software gives us very, very quick feedback on the design. So we get the sizing estimates based on what material systems we're going to use. Those are determined by if it's a capacitor dominant, inductor dominant filter, and the physical size constraints given to us by the customer. You'll see here I have labeled high DK That's dielectric constant of the material, and DL is dielectric loss. Those are just very broad rules of thumb on what kind of material system we select for the type of filter. And then our CAD software will actually build that out into this image you see on the right with the inductive elements in light green, and then these capacitive elements, and then these vias in between those elements to build up this filter. You can see the schematic there, but when we actually build it, the first build will actually generate 3 physical devices. This is to account for manufacturing tolerances. They're very subtle, very intentional frequency shifts to account for those tolerances. And I've yet to hear of a build that didn't hit the customer's specifications in the first build. So almost always it takes just simply one build, and then one of those 3 physical devices will match the customer's specifications. More on manufacturing. These are just simple illustrations, but to break it down into simple steps again, what you notice first off is that there's no heat required, no formulation of a ceramic, where you must first consider particle size, density. You have to stack those layers and, fire into a monolithic block. There's shrinking involved. Yes, it's tightly controlled and can be controlled. And I just wanted to bring up with MLO that thermal exposure variable is not included in MLO manufacture. And so that contributes to the tight tolerances that we have. Again, starting off with a low loss material, do our initial metallization pattern, adding the dielectric layers, putting the stacks together. Connections between the stacks, we use vias, blind or through hole vias, as you can see on the image on the bottom right. We can get a connection from metal layer 1 to M6 using those vias. So again, no thermal element involved, simply building a double layer PCB, repeating that multiple times with materials that we've modeled and simulated, and creating vias to connect those multiple stacks and those capacitive and inductive elements. So this is a bit of a motherhood slide, but high order filters, the advantage is that we're going to get these high order filters in small packages. We can use intentional values of capacitance and inductance, or we can actually manipulate the parasitics of those elements and to build up a filter or another integrated device. But as opposed to, they can be made and built up using discrete devices, but one of the advantages we have is, we don't need those standoff distances. They're very high density, low profile, less than one millimeter on many devices, which becomes important when considering crossband interference. The fact that we're laser direct image and that there's no high temperatures involved, there's no dielectric K variance involved from, like we see, from firing ceramics. These advantages in tolerances and repeatability means that simply, there's virtually no tuning involved. The material systems that we use has closely matched TCE to boards and thermal compression of expansion and low concerns across a wide temperature spectrum from electricals as well. It passes ASTM for outgassing, so these are acceptable for spacecraft, high altitude applications. We mentioned the large wafer starts, and that's where the economy of scale comes in. LTCC wafers may be 9 inches or a little more, but certainly not in the realm of what I showed earlier. They'd be 18 by 24, making the 180K 0402 devices. Okay, so this shows a quick exercise we performed to show the size benefits. This might also make your purchasing department or component engineer's job a little bit easier too. Far less part numbers, data sheets to keep up with, right? For this filter that we're looking at, it requires 23 capacitors and 12 inductors. And we just, let's say you find those in EIA 0402, again, 1 millimeter by half a millimeter, and let's assume a keep out of 10 mils. Laying this out in the circuit orientation at the top, we'd take up, 25 millimeters by, 3.5 millimeters there. And you'll see below the note about the thickness and how 0402's EIA is 0.56 millimeters. This filter, this MLO filter we have is right at 0.56. And even though the specification says, less than 1 millimeter, just going through our data sheets, the typical height is that 0.56 height that you'd find in an 0402 package. Okay, now that we know what MLO is, how it's made, what it can do, let's look into some non-standard modifications that we can take advantage of, knowing that these devices are packaged in PCB. On the left, we have a standard MLO, and below we've added an alumina cover to increase its power handling. This stems from knowing we have such a high density of components, and that we know we're going to have a benefit of even distribution of heat across those elements. You'll notice on the cover, I showed polarity markings on a filter earlier. The alumina cover does not have any markings, but a regular production device would. The great people in the lab, they just, they can just tell by a termination pattern the polarity. So, but they would be marked. So in addition to a heat shield, we could also terminate resistors on the top of the device, and we'll get into what those modifications can afford us. Okay, so here we can see on the image on the bottom left a filter, and you can see those inductive elements generating most of the heat in the uncovered device. Reducing this thermal isolation would mitigate failures and adverse use conditions, but it's also worthwhile to consider signal integrity between even distribution of heat. We're going to preserve the propagation speeds and those other things. In the middle, we can see that the heat building up on the alumina cover, and then in the right, we'll see the heat being distributed across that whole alumina surface. And it should be noted that filters with heat shields would need to be redesigned to account for the capacitive coupling there. And here's a chart of the data. We took power measurements at high and low frequencies to confirm, just again, that we're working with low loss materials at the interface of the dielectric and the metallization systems. Since the curves are relatively close, we just know the losses are low, and is the reason why we have the two frequencies. After the first frequency with the alumina shield, we realized that the performance drastically improved, and is the reason why the subsequent data points, start at 3 watts and 4. We just went ahead and jumped from 1 watt to a higher power to just consolidate some of the data points we get. And you'll notice, of course, there was a second material heat spreader that we use, aluminum nitride. It was very brittle, difficult to work with, and so we decided that alumina, because the performance is similar between the alumina and aluminum nitride, that for any non-standard high power devices, we'd go with aluminum. Okay, incorporating resistors. So what we have here is a Wilkinson-Splitter divider, and this is just show again the physical advantages in terms of size of surface area that we're taking up on designs. You'll see the chart on the left is the spread of the data to the right of it, which shows the individual device performance. And yeah, just the sizing differences are very huge. And then I've added a blown up image of that MLO with the resistor on top, just to show detail. And then of course we have you can see there that the coupler with the external resistors, replacing a 20 centimeter long device, had much improved insertion loss. Couldn't find the chart for it, but I was told that it was 5 times improved insertion loss on our coupler compared to the original solution. Moving away from advanced capability in MLO, we're just going to consider standard components next, and comparing the performance of MLO devices to alternate technologies. For diplexers, for a diplexer, LTCC diplexer comparison, you can notice that we have a slight volume benefit there straight out of the bat. Insertion loss at the high band is much lower than the LTCC high band insertion loss. This is because copper thickness of the MLO can be around 10 times thicker than the electrodes of LTCCs. That's improved skin effect and at those frequencies, and that's why you're going to see that advantage there. Attenuation out of band is better than the LTCC, and while there was no VSWR info, we measured it on our devices, and we believe them to be statistically accurate, and so added them to the chart there. Comparing a discrete device and an MLO inductor to thin film, multi-layer ceramic, wire-wound ceramic inductors, comparing inductance value, current capability, Q factor, and frequencies. We can see that MLO really has a well-balanced offering here, and where it really shines is when we consider characteristics typically not found on data sheets, or maybe hard to find on data sheets. TCE mismatches, performance across temperature. The MLO is really, very small and robust. Again, we mentioned the TCE is very closely matched to boards. And if we take, for an example, a wire-wound device, there's a possibility the windings could be compromised by pick-and-place machines or mechanical damage. And also we mentioned the tight tolerances inherent with the MLO due to laser direct imaging. You can see the internal metallization pattern of our inductor there on the bottom right. Just want to bring up again, no thermal formulation element in the process. And the high SRF, just implying that we have low parasitic loading. The main point to see here is that the Q factor is quite good across frequency, and if we account for the overcurrent handling, we arrive at a very robust device. You can see our data sheet specification of 290 milliamps at a 15C rise. This is typical for component manufacturers to select an arbitrary specification on temperature rise. And we've put data for multiple data points for 0.3 and 0.6, 0.3 being at our specification, and then 0.6 milliamps being double our specification. You can see that at double of our 15C rise, we're still under 60 C rise of temperature, and that to us is especially if we're considering use at ambient temperatures. Our operating temperature is 125 C. We still find this to not cause red flags for us. Is at 2 times current specification, we're still maintaining the Q, and just want to show here that we have a very robust device across temperature. We looked at a diplexer, inductor, so we're going to look at a filter here. The electrical response is very similar. It's uncanny. The insertion loss and return loss charts that you see there, and again, the size discrepancy, the small size advantages is what we want to highlight here. We've maintained the performance, the frequency response, and doing it at 5% of the equivalent LTCC filter. And we're combining here a high pass and then a low pass filter to generate that response. And those devices, you can see the dimensions there. Again, this is again thanks to those material systems, the low loss material systems I mentioned earlier, the models, the simulation software that we have, being able to predict the behaviors and the orientations of those filters, the tight tolerance on manufacture. That's what really contributes to integrating those capacitive and inductive elements into very small form factors. And just to close, just want to say, if we compare it to LTCC, there's none of that firing formulation of the ceramic involved. That's an advantage for MLO. All laser direct imaging, not using any liquid metals, no firing or shrinkage variables to consider on the construction of these devices. And what we're looking at in terms of what may new products be, what's on the roadmap is there's those we could build up more stacks. We can make it larger. We could add more components, higher filters, larger, and that would give us larger capacitance and inductance values for lower filter responses. And there's the capability we saw to have solder pads right on the device, and we saw resistors are easy enough. The heat spreader is easy enough, and we think adding active components would be good, and essentially come up with the system and package substrate there. And that's it from me. I don't have a thank you slide to leave it on, but I'll just leave it here on the summary. Thank you.
Thank you, Daniel. Great presentation. Yeah, again, if anyone has any questions, please type them in the chat box and ask Daniel. One question I have is on, I think it was on slide 11, you showed some of the power and some of the heat coming out of upwards to the aluminum cover. And are you seeing any heat going down through the laminate on that as well, or any issues that the customers should have in terms of solder attachment, or in terms of how that would affect either the thermal dissipation or performance?
Yeah, unfortunately, I don't have that info, and I don't know if we did check. We just combined these IR signatures to the power charts that we saw, and what we're gonna have to assume is that there's very small heat flow going on.
Okay. Alrighty. Got another question coming through. What organic dielectric material are you using in diameter of the stack blind vias?
I have to get back with you on that. I have to ask the design guys. I'm not intimately involved in the selection of the materials, but I can get it for you.
Okay. Thanks.
I just don't know.
Ready? Everyone else in a minute or two. All righty. Not seeing any other questions coming through. Thank you, Daniel, again.
Thank you.
Pass it back to you, Tom.
Our next speaker is Ron Demko from AVX. He graduated in 1982 from the Clarkson College of Technology with a BSCE. He's currently an AVX fellow and manages the TSG team at AVX headquarters in Fountain Inn, South Carolina. This role centers on projects ranging from simulation models for passive components to product support, new product identification, and applied development. Prior to that, Ron was the EMC lab manager at the AVX Raleigh, North Carolina. This lab concentrated on subassembly and passive component fixes for harsh electrical and environmental systems. Before the EMC lab work, he held a applications engineering position at AVX. Product work included integrative passive components, EMI filters, and transient voltage suppression devices. Before joining AVX, he worked as a product engineer and later product engineering manager at Corning Glassworks in the electronics division. In his role, he supported production, sale, and development of pulsed resistant capacitors, high temperature capacitors, and radiation resistant capacitors. He developed high frequency test methods and co-developed high temperature test system. I would also like to say Ron has really supported IMAPS, but he's also supported my Tom Green on the CMSE components for military and space electronics. He's given many seminars on capacitors, and he's a world traveler. So, all right. And his title of his paper is High Temperature Passive Component Transient Voltage Circuit Protection Devices.
Okay, thank you very much, Tom. I really appreciate that. I have to admit, during Daniel's talk, I lost power again. So the joke is when we had our pre-run, when we had the practice run of this event, I happened to lose power again then. Well, I told my wife that we're going to buy a Honda generator, and we did. And I didn't plan that we'd lose power again so quickly because the generator is in the back of her car. So I'm hoping that our power stays on. I've got my headphones on. I could switch over to the phone if things happen again, but it's amazing. I lost power twice in a few weeks. So our title is High Temperature Passive Components. What we'd like to do is give an update on high temperature transient voltage protection in particular. And there's a couple of reasons why this is becoming more important. I'd like to give a little bit of a background on this, though. The high temperature PR mainly is given to that of semiconductors, and rightfully so with what GaN is doing and some silicon carbide and even some other high temperature extensions. So, you know, there's not an awful lot of press out there on passives. And the press that is out there typically goes to capacitors and resistors. So, you know, that progress is quite well documented. It's in the form of higher temperature dielectrics and some packaging and some interfaces. But, you know, that's probably 90% of the passive component publicity. Well, perhaps some inductors get some other publicity as well, but the world of transient voltage suppressors, the TVS device, really gets very little amount of press. So because of that, we wanted to do this, and you know, as you heard through Jay's talk, you know, GaN is going to be throughout base stations and 5G and all of that, and a variety of other power applications. Things are going to run much hotter, and those interfaces might have a true need for transient voltage suppression. So that's why we wanted to give this update on what is out there. It's available by many manufacturers. Those manufacturers produce both onshore in America as well as Europe and Asia. So this is truly a worldwide improvement in the world of transient voltage suppression. What we are going to do, our outline is really simple. We've got six and subtopics and then the summary. We have an introduction to circuit protection. We'll look at varistor options. There's two different types of varistors that are most common. Then we'll look at transient voltage suppressor diodes, TVS diodes, high temperature tolerance between those two technologies. We'll look at some derating and selection, and then MLV options, then do a quick summary. So the world of transient voltage introduction here. So what do these things do? Well, they redirect charge, and the key terms that we'll look at are on the bottom. The TVS is a transient voltage suppressor. Transient voltage suppressors that we'll talk about could either be a multi-layer varistor, that's MLV, a single layer varistor, SLV, and of course ESD is electrostatic discharge. But what is occurring here is that in some end system there's always a transient, and that transient may be induced from some inductance, inductive load turning off, or it might be an external transient, it might be a lightning wave, it might be someone walking across the carpet and where there's a lot of static electricity and they touch the computer. So it's this peak of the transient is what we're trying to get rid of, and it's clamped ideally to ground through this this device here. And some of the things that are important is when that device begins conduction. That's the breakdown voltage, and how much current could this thing take? How long does it take to turn on, and what amount of energy could it withstand? So we'll look at all of that a little bit, but the key is that transients could either be positive or negative in nature. They could be a result of ringing. They could be very complex waveforms. They could be repetitive or single shot in nature. So we have to be cautious, particularly about the energy rating of the transient protection device, because it's very easy for these things to get burned out, since it's always a little bit difficult to determine the type of threat that they are going to exist in. So the first thing we'll look at are the three most common types of transient voltage suppressors. On the right is the TVS diode. In the center is the single layer varistor. These are very common to what you might have on your AC power strips at home. If you buy a really expensive AC power strip, you'll notice that they talk about these wearing out. They actually say that this type of device could withstand 10 or 100 or 300 pulses of a transient, and at which point they should be considered bad and non-operative and thrown out. That's actually true. These devices wear out. And one of the biggest concerns with designers when the multi-layer varistor came into the market perhaps 20 or 30 years ago was the fact that it had the word varistor in its name. And the biggest mountain to overcome was to prove that the multi-layer varistors do not wear out like single layer varistors, even though they're based upon the same material system. So we'll talk very little about single layer varistors. They're actually wonderful devices. They truly have a place in design. But for the most part, what we'd like to talk about is these technologies here, the smaller TVS multi-layer varistors and the TVS diode. So like we talked about, we have to explain why does a varistor die? Why does a single layer varistor die and wear out? Why does a multi-layer varistor not wear out? And it all comes down to the material system. If we were to very much simplify the building of a disc varistor, a single layer varistor, first off, you could see that there's just one layer of dielectric oxide here, and that's the varistor device. And then there's a metallization on top, a lead on top, a lead on the bottom, and that's where the energy is dissipated. Well, those grains are actually quite inexact. It's almost is in a very simplified sense. Imagine pouring flour into a coffee mug, putting a little bit of water in the coffee mug, maybe a couple of teaspoons, and compressing it with 5 or 10 tons of pressure into a block, and then firing it. Well, basically, the grain size is not that well defined of the single layer varistor. That's actually a very simplified version of the process, but it's quite accurate in general. So a multi-layer varistor is quite a bit different. You can see our depiction here of the grain structure, and truly these grains are all the same size. With them all being the same size, they have the similar electric field strength between them. So the multi-layer varistor, when it does receive strikes, the amount of energy and the heat dissipation is equally throughout the total volume of the part, whereas these devices have thermal stressing and excessive E-fills that causes the wear out. There's tons of data by all manufacturers of the multi-layer varistors' actual reliability. So that's something that's out there. We have an SEM, which is a little bit harder to see the grain consistency of the dielectric, but indeed it's there. If you're not used to reading SEMs, that's basically a good cross section. So while we're talking about the MLVs, the multi-layer varistor, each one of the grains, and there's millions of grains in between these electrodes. These are the electrodes here, and this is actually the oxide in this region. All of these diodes are in a series parallel combination, and because of that, the power is dissipated through a very large series parallel array. Generally, that means that the varistor has a much larger active area to dissipate the strike, and that means that varistors, in fact, could take tens of thousands of strikes before wear out. And as opposed to that, we have a diode with a lead frame, and as Jay talked about, an organic package. And these two devices are actually connected back to back with a bond that has some amount of inductance. But the whole point is the amount of volume where the transient is dissipated in the diode is quite small. On a comparative basis, the PN junction is about 5% of the volume of the total package. And then the depletion zone within that PN junction is going to be quite small. So you could see that the amount of power dissipated per unit area or per unit volume is greatly higher in the TVS diode. Now, that's not to imply diodes are a bad device. They've got a great pedigree. They've got a great history and all of that. But there's some differences in the diode TVS and the multi-layer varistor. There's alternate ways to package the diode, and in this situation, you actually see the diodes back to back. But basically, the point is that diodes are a good option. They're not always the best option, but they're a good option. There's a very wide range of packages and voltages and energies available. They also have a lot of different qualifications, whether it be flight and high rel or industrial or even consumer, the lowest of demands in terms of reliability, but the most aggressive cost. But regardless of what those grades are, the energy is always is dissipated in that small depletion zone, and it's quite dense as compared to that of the multi-layer varistor. So what we'd like to do here is let's compare the use of the TVS diodes, and something that's important is to look at how the parts conduct their charge. What we're seeing is a unidirectional device, and at some point there's steady voltage on it, and basically this is the off state of the device. It's very interesting and important to know the amount of leakage current through this device in its off state, because commonly they're either in parallel with the power from power to ground or signal to ground. So we don't want a large resistance flow there. We want to have a very low leakage. At some point, the device turns on. When we have an increased electric field, we start taking current. That's usually the breakdown voltage. It's commonly 1 milliamp in magnitude. And then there's some clamping voltage. Usually that's defined with a particular waveform. It happens to be an 8x20 waveform. and it has a specified amperage depending upon the type of device. But this is really, what's going on in a diode, right? There's a steady state low voltage on it. At some point in time, that transient hits it, it starts to turn on, and then it clamps at full conduction. Now, what isn't necessarily as apparent in all of the specification sheets is that the power of the diode doesn't necessarily stay the same across temperature. And in fact, not only does it not stay the same across temperature, depending upon the diode type, but it doesn't by the manufacturer, or the power rating. So this is a relatively high power device. We can see that there's 0 derating till about 70 degrees centigrade, and then the linear derating to 150 point. And here is a lower power TVS diode that starts derating right at 25C. Now, this isn't to say that diodes are bad. We don't mean that at all. As long as you understand what that derating curve is, and as long as this derating curve is above your power need, you're in good shape. But in some cases, these cost points to be above that amount of power that you need gets expensive. So that's how the multi-layer varistors got more interest at high temperatures. And just as a point of interest, as you go about your daily life, you might have 1,000 multi-layer varistors that are in your life that you don't know about, that are protecting your I/O port on your PC, or they're protecting the charge port on your cell phone, or a whole bunch of other things, including your vehicles. So these are kind of ubiquitous throughout the electronics that we're dealing with. Now, a couple of things that are actually negatives in some ways to the multi-layer varistor. Unlike diodes, these have to be bidirectional. So there's no way you could ever stop a reverse voltage going into a charge port with a multi-layer varistor. You could stop the transient because that's parallel to ground, but you can't do a good job in series blocking anything really with this device, as you can understand. But there's still a wide range of packages and voltages and energies and all of that. They have a very fast turn on time, which is quite important. And the fact that these are multiple layers implies that the current is divided as the current comes up the termination and goes across the device. Also, there is a very low inductance in the part. So these generally take excessively large amounts of transient current without problems, and they also can turn on very, very quickly. Now, as we talked about the VI curve before, in a couple of slides, we'll look at what the VI curve looks at for the varistor, because relative to the diode, varistors have a soft knee. We'll talk about that in a bit. But let's do a blow up of these cross sections here. And what this shows is an important feature of the device. As we said, that the parts are made up of these individual grains, and each individual grain actually has an interface, and that boundary interface actually works as the equivalent of a back-to-back diode. Its resistance will vary proportional to the electric field. So when we create a varistor, we have to have a certain number of series devices, series diodes, to get us our voltage, and we have to have a certain amount of parallel series stacks to get our energy rating. So this is basically a better representation of the exact physics of what's going on. It's very simplified, but nonetheless generally accurate. And you can see that this is our bidirectional VI characteristics of the part. So some of the main specification parameters that you'd want to run into would be, when we create our spec, we have to have the working voltage. We always want to have our working voltage of the varistor higher than that of course, the circuit. Breakdown voltage is at the point at which we conduct at that 1 milliamp point. These are the points where we clamp, and then there's some additional pulse requirements that could be out there, and this one happens to define that of jump start, which is transient. It's a transient for automobile type applications. But let's get back to that nebulous VI curve and the comment I made about the soft knee. And what we're showing here is that well, regardless of what transient protection device you have, a diode or a varistor, it will chug along fine up until you get to the E field, the electric field, what actually turns it on. Now, that turn on point is much quicker for the diode than it is for the varistor. The formula is I equals kV to the alpha. The alpha is not as high for the varistor, and for that reason, the varistor turns on at a softer knee, so to say. There's been work by all manufacturers to drop the actual turn-on voltage, full turn-on voltage, the clamping voltage, and that's in fact been quite successful. So there's two things that you could say that are being broken, right? Multi-layer varistors do not wear out, and multi-layer varistors clamping ratio generally is getting better, but it's still not as good as the diode. Now, there's other reasons to think MLVs are great. In fact, this is kind of one of the main points of the discussion here, is that if we're to compare a varistor in blue to that of a diode and its survivability, given a variety of transient pulses with increasing temperature, you could see that the diode starts to degrade and actually have poor survivability with increased temperature and pulsing. So that's why it's very important. You know, your laptop might survive great at 25C. You might get it out on your work site if you're outside doing work. It might be, you know, 35C or whatever in the sun, and you're going to start seeing ESD becoming more of a problem, and those ports having potential failures. And the same is true for your cell phone, and imagine the situation in your vehicle. So potentially that is a problem with the TVS diode. What I wanted to do is bring up some other things about the varistor that may imply that it's a very good choice for circuitry. In fact, high temperature circuitry as well. If you're protecting a port with diodes commonly have quite a low but very controlled capacitance. Well, you may want an EMC capacitor on that port as well. And the varistor, which we represent by a back-to-back diode, actually is the equivalent of a capacitor and a varistor in parallel. We'll show that schematically in the next slide, but you can see why this actually has a some amount of capacitance to it. If we were to cut apart a capacitor structure would look just like this. It's just a different dielectric. So what we could say is that the varistor will always be smaller than the diode and the capacitor combo. The varistor can in fact be placed on your EMC capacitor's pads. So it's a very easy device to retrofit with should you have a problem with the diode not being fast enough, with the diode burning out with temperature, etc. And in fact, we could actually show the S21 characteristics of that capacitance of the varistor, and you could specify the actual EMC worth of that device. Last couple of slides, what we want to show is a typical diode rating. And in this case, I took the small signal diode and I compared it to a small signal varistor in blue, and these are the same for all varistor manufacturers. And then there's some varistor manufacturers that have gone to 150. There's some that have gone to 175C, but in general, the power derating curve for high temperature varistors is exactly this line, 0 derating across temperature to its max temp point, and then linear derating at some point beyond that. This just shows some of the inputs to those graphs. And what this really means is that the varistor can always be smaller for a total or for a direct power comparison against the diode. And that small varistor, it will actually have a better turn-on time than the diode. So if we look, if what we have to do to look at the protection efficiency of a port is to look at turn-on time and the actual knee of the VI curve. So the last page, well, actually 2 pages. The last page shows the varistor's schematic symbol. It shows how it will clamp that transient upon incoming. In the off state, it looks like a capacitor. In the on state, it's a voltage variable resistor, and that's what what is shown here, and you can see the associated signal that would be going to be compatible with each one of those states. These are just interesting. They happen to be power derating curves of different types of varistors, but you could see the point that they have zero derating across rated temperature, then linearly derate. So what we'd like to say and summarize is that TVS suppression using single layer varistors, multi-layer varistors, and TVS diodes it's always going to be out there. There's always areas where each one excels. So it's good to know the power derating aspect and what could get you in trouble. The MLVs and TVS diode was discussed. Generally, I think MLVs are much more resilient across temperature as well as over strikes. We talked about some of those different derating curves, what to be careful of. We gave you an example of that high temperature performance and talked briefly about some selection. Thank you very much, and I hope that this was of some interest to you.
Thank you, Ron. That was a great talk. You have a question that came through. Are the MLV specified to any military applications or specifications?
Yes, no, they are not. They have been used in a variety of spacecraft. In fact, they tend to have, they have some radiation stability characteristics, but there are no military specs. There is one military drawing. There's only one supplier on it, but no mil specs.
Ready? Another question, are there separate families of devices designed for 225 plus operating temperatures?
Yes.
This is the baseline temperature used for the high temperature industry for such applications as downhole oil gas exploration, monitoring, and geothermal systems.
Yes, there are. Those material systems are different. They're still zinc oxide, and there are at least two manufacturers that have the exceptionally high temperature characteristics of those devices. What's accelerating the use of that is GaN in a few different for a few different reasons. But yes, there are high temp versions of this.
Okay. I know you had a couple of slides on package sizes. I guess what's the smallest sizes that we're getting down to as substrates getting high density? Or?
Yeah, they can get down to an O201, and that gets very interesting because O201s actually in some instances and scenarios could take the place of an SMB sized diode. We have to be careful though. It's not always going to take that and replace an SMB diode, but in some cases, you could see a reduction of 95% of the volume of what's needed. So and I'm not in pricing by any way, but I know that for them to get into vehicles and to get into cell phones, they have to be quite aggressively priced. So it appears to be, from an engineering point of view, that they're smaller and they're as cheap, perhaps cheaper, and they have equal to or better. In fact, I'd vote for better performance in many scenarios.
Ready? Not seeing any other questions coming through on the chat box. Another couple seconds here. Alrighty. Well, thank you, Ron. Great talk.
Thank you.
Pass it back to you, Tom.
Okay, our next and cleanup speaker is Dr. Rick Sturdivant. His presentation is called 5G and 6G, Phased Array Packaging Challenges and Opportunities. Dr. Sturdivant is a recognized expert in the fields of electronic packaging and phased arrays. He's published over 50 journal and conference papers and authored several books. His latest book is Systems Engineering of Phased Arrays, Artec House in 2018. He's worked for Raytheon Systems from 1989 to 2000. Since 2000, he started several successful technology companies providing solutions for wireless, microwave, millimeter wave, and high-speed products. He's a lecturer at Azusa Pacific University and founder and CTO of MPT Inc., which provides phased arrays for communication and radar application. Rick holds the BS degree in electrical engineering from California State University at Long Beach, BS in religion from Vanguard University, and an MS degree in electrical engineering from Cal State Long Beach, as well as a PhD in systems engineering from Colorado State University. Okay, Rick?
Okay, great. Thank you for that introduction, Tom. I will go ahead and share my screen. Okay, so my talk is about something I'm pretty excited about because I've been working in it for most of my career at various times. And it's actually the combination of two of my passions, which are electronic packaging and phased arrays. So it is something that I'm enthusiastic about talking about and interested in. It's the kinds of things that I think about in my spare time. Let's see. I'm going to first talk about what's a phased array and why should you care, right? What's the big deal about phased arrays? And then I'm going to go into some typical applications of phased arrays, and just so you get a familiarity of how they're used. And then talk about 4 packaging challenges and opportunities. If there are challenges, then what that means for engineers is it means there's opportunities, job opportunities, business opportunities, and intellectual pursuit opportunities. So that's why I think identifying the challenges is a first step that we do as engineers, and then we come up with the fixes, of course. So in order to understand phased arrays, maybe the best place to start is to talk about this thing called an isotropic antenna. An isotropic antenna is a theoretical thing that doesn't actually exist, but we use it because it's helpful. And what it is, it's an antenna that radiates energy in all directions. Most people are familiar with antennas because they exist in your cell phones, or you're familiar with an antenna that sits on maybe on the top of your house or your neighbor's house to receive satellite TV broadcasts. But this theoretical thing called an isotropic antenna radiates energy equally in all directions. It's sort of like if you drop a pebble into a pond and you watch the waves from that pebble drop into the pond move away from the center where that pebble was dropped. Those waves are going to move away from that center point where the pebble was dropped equally in all directions. An isotropic antenna does the same thing, except it sends out radio waves equally in all directions in 3 dimensions, not just in 2 dimensions, like in the pond pebble pond pebble example. So let's see. So next slide here is what a phased array does. What a phased array does is it directs energy in it focuses the energy out of an antenna in a particular direction. Rather than radiating energy in all directions equally, it will focus energy in one particular spatial direction. And as we'll see here in a moment, that's a huge benefit for some particular applications, such as, let's say, radar, where you want to shoot a little radar beam at a particular target to interrogate that target or determine the range. Phased arrays are very useful for that. And as you can see here in the bottom left, that's an example of a 4-element antenna beam. It turns out if you put individual antenna elements that radiate energy in almost isotropic in an almost isotropic manner, and you put them together in a special way with a special amount of spacing between them, and feed them energy, radio frequency energy at the right frequency in the right phase, Well, by cracky, if you don't get an antenna beam out that focuses the antenna energy. And what's shown there on the top right is the radiation pattern from a phased array. It shows that there's a main beam right at 90 degrees, which is off of the face of the array. And as you move away from that, the main beam there, the energy that's radiated from the antenna begins to fall. And as you get further away from the main beam, the energy levels drop to for some phased arrays, they can be down to 20 or even 30 dB below the main beam. So you're very much focusing the energy in one direction. And on the bottom right is shown there is a symbol for antenna elements. What it shows is a number of elements. It looks like 8 elements in a signal combining network that combines a signal so that you do get this focusing of the antenna energy in one area. And then what ends up happening in a typical phased array system is you have, of course, the antenna elements, or shown here as these little things that look like Ys here. They represent the antenna elements, the individual little antenna elements that make up the array. And behind them are these phase shifters. It turns out the phase shifters do another little wonderful thing for phased arrays, and that is they allow the energy that's the focus beam to be steered in a particular direction. So if you can add a linear progressive phase behind each one of those antenna elements, not only do you focus the antenna energy, but now you can steer it around electronically. Instead of having to have a mechanical dish that you spin around to steer an antenna beam, now you can have a flat plate of antenna elements with phase shifts at each element, and now you can have a beam that you steer electronically, which is, of course, much more reliable than a mechanically moving antenna. And then in these systems, there are phase shifter controlled circuits. It shows a transmitter there in this particular example, but you could also have a receiver and steer a receive beam and receive signals preferentially in the direction that you steer your antenna. So that's a little bit of a background of what phased arrays are. And here's some typical uses. The TIPI-2 radar has a phased array. It's huge, as you can see there on the top right. That's the radar that the U.S. has deployed around North Korea to detect missile launches by the North Koreans, and that's actually deployed around the world. The TIPI-2 radar at various locations, and the U.S. and our allies use this system to detect intercontinental ballistic missile launches, and it steers a little pencil beam of energy around using phase shifters, and it has a behind the face here. This is the face. Whoops. This is the face of the array here, and behind it are antenna elements and phase shifters steering around some beam that looks a very long distance away and can detect missile launches. Pretty cool. And then what's shown here is in the next one is an airborne phased array on a fighter plane, and that phased array is able to steer a beam up and communicate with a satellite. It's able to track other aircraft. It's able to deliver weapons such as missiles and communicate with ships and also ground troops. It happens because it has a phased array in the front of that fighter plane, and it can steer multiple beams at the same time at multiple targets. It focuses those beams, so it has multiple beams focusing energy at multiple targets, performing radar functions and communications functions simultaneously. So, but there are not only military applications, but there are non-military applications. And one of them, the big hot one now, of course, is 5G. We're going to talk a little more about that. There are also Internet of Things applications, medical applications, internet access applications. For instance, the Zephyr Airbus UAV could use a phased array and and backhaul and front haul for communications. All use or have been proposed to use phased arrays. So this is an interesting slide that shows why 5G systems need phased arrays. Everyone's familiar with previous generation 3G and 4G communication systems. You've seen the antenna towers near your home, and the antenna towers typically have an antenna on them, and those antennas radiate energy in a very broad antenna beam. And for instance, if you have a user here represented, being communicated with, represented by these dotted lines, that's a good thing, but you're also transmitting energy in these other directions where there aren't any users at that particular time. That energy is being wasted. It's not being put to use for the user that you're trying to communicate with. And so the phased array comes along and says, well, okay, instead of doing that, I'm going to steer a beam on purpose to a particular user, and I'm going to focus all the energy that I would be sending in multiple directions just at that particular user, and then I'm going to apply that method to steer antenna beams, individual antenna beams to multiple users, and the net result is increases in data rates of 10 to 100 times greater than what users are able to experience with 5G, with 4G systems. So it's a huge increase in data bandwidth to users. Here's an example of a phased array that was developed by a group of researchers. What it shows is as you can probably tell from the slide, there are a bunch of small little squares. Each one of those squares is an antenna element at 28 gigahertz. And you place those antenna elements next to each other. It's at a special spacing that we'll talk about here in a moment. And phase shift relative to each one of these elements, and you get antenna beams that you can steer around, just as we mentioned earlier. And that's what this unit does at 28 gigahertz. It's been realized in silicon-based integrated circuit technology. One of the interesting things is that the public-private partnership in Europe published a report not too many years ago where they said something very interesting. They said that we assume backhaul and access links share the same air interface, and all network elements, including base stations, access points, and user equipment, are equipped with directional steerable antennas and can direct their beams in specific directions. This is from the 5G public-private partnership in Europe. What does that mean? Directional steered antennas means phased arrays. So not only will the base stations and the access points, but also user equipment, which means cell phones and smart devices, who are going to have phased arrays on them. So this technology that used to only be used in high-end military systems is now going to be used in multiple applications. So phased arrays are going to become an important building block for future communication systems. They already are, and they're just going to grow in the level of critical function they provide in those systems. So if that's true, maybe we should look a little bit at what the typical block diagram of a phased array is. And so that's what I've attempted to represent here, is a very simplified view of a phased array, so that you can see where the packaging opportunities may be, where the packaging challenges might be. And so what's often in a phased array, or very, very often, are individual antenna elements. That's almost like a requirement for a phased array. And then behind them are typically a thing called a transmit receive functionality, and that could be a transmit receive module. It could be an individual integrated circuit that provides the transmit receive functionality. And we don't have the time to dive into the details of what's inside that, the transmit receive functionality, but it has, performs very complex functions, including the phase shift and other amplification of signals. Then behind that is an item called a power divider network. And the power divider network takes an input signal, input transmit signal, or receives or combines a receive signal and distributes it to the rest of the modules and to the antenna elements in the array. So there are interconnects between the antenna elements and these modules. There are amplifiers in the transmit receive functionality, and they could be high power amplifiers. So so now there's a heat dissipation opportunity there. You've got interconnects that have to operate at millimeter wave frequencies and connect between antenna elements and integrated circuits. You have wire bonds that need to function at millimeter wave, microwave and millimeter wave frequencies, or flip chip interconnects possibly. You have radiation concerns inside of these circuits, the power divider networks, which are the beamforming networks, the manifold, and in the modules, and in the antennas. There is unwanted radiation. And guess who gets to fix that? Usually the packaging engineer needs to fix those undesired radiation effects in conjunction with the electrical engineers. There are material concerns, and now you've got millimeter wave frequencies bouncing around, and you need to use dielectrics that have the right loss and can support have the right dielectric constant that's required for the particular system that you're trying to realize. Sometimes you need a low dielectric constant. Sometimes you need a high dielectric constant. And again, those get back to packaging concerns. So these systems have multiple areas where the expertise of packaging engineers is critical to the success of the development of these phased arrays. And one of the packaging challenges is packaging density. And I'm going to explain fundamentally why this is a problem and becomes a bigger problem as you increase in frequency. What's shown here on the right is some antenna elements in a phase array. So these are individual antenna elements combined to form an array. And they're spaced by some distance d from each other. That's the pitch between elements. It turns out that that distance has to be some fraction of a wavelength, and typically it's on the order of 0.5 wavelength, so like a half a wavelength, or maybe 0.8 wavelength, or something like that, to avoid something that's undesired called grating lobes, which is beyond the scope of the talk here. But that spacing is required for the proper function of the array. And guess what? Since it's a function of wavelength, as you go up in frequency, that spacing gets smaller and smaller, which means you have less area now for the antenna elements, for the packaging, for the integrated circuits, and things become more difficult. Now your power density goes up, dissipated power density goes up. And as you can see on the right there, at 20 gigahertz, the distance between antenna elements is 5 millimeters. By the time you get to 40 gigahertz, it's 2.5 millimeters. And at 80 gigahertz, you're at 1.25 millimeter pitch between antenna elements. That means you have significant challenges. And of course, those numbers assume half wavelength spacing, which is very, very typical. You don't have to have half wavelength, but it's extremely typical to be in that range of half wavelength to 0.8 wavelength. So that's one of the challenges, is how do you fit everything in there? How do you dissipate all the power that you have in that? One of the other problems you have when you've got that kind of packaging density is the interconnects. And what I've shown here is simulations of wire bond performance as a function of frequency and flip chip performance as a function of frequency. I love wire bonds, but wire bonds can be difficult to get to work properly at microwave and millimeter wave frequencies, where a bunch of these 5G phase arrays are going to be deployed. You can make them work, and so some people will go to ribbon bonds, which is an improvement and helps, certainly. but flip chips become an important option there. And you can see over to my bottom right graph there, the benefits of flip chips on performance of the interconnect. It shows their return loss as a function of frequency, which is analogous to impedance match. And as you go out to 70 gigahertz with flip chips, you can still maintain good interconnect. So you have to pay attention to interconnects in these systems because of the frequency range. Another challenge is heat dissipation. What I've shown here is a gallium nitride high power amplifier. And if you take the heat dissipating elements in this high power amplifier are these transistors here, these field effect transistors on the output stage of this amplifier. And if you go through and you calculate the heat density coming out of these amplifiers, you come up with 2.5 kilowatts per square centimeter. To give you an indication, if you take your clothes iron and turn it up full blast, the heat density coming out of your clothes iron is going to be less than the 2.5 kilowatts per square centimeter by a large margin. So the heat density coming out of some of these gallium nitride devices is higher than the heat density coming out of your iron that you iron clothes with. It's a significant amount of heat flux that must be dealt with. That the heat needs to be removed rapidly from where the chip is located, spread as rapidly as can be, and then conducted away to a cold plate, to some type of thermal radiator or other method to move the heat out. And that's guess what? That's an electronic packaging challenge. And the electronic packaging engineer will have to work very closely with the rest of the design team to help solve this heat dissipation problem. I was talking to a friend of mine who's developing a phased array for 5G. And guess what he said his biggest problem was? Thermal, heat dissipation. His biggest problem. It's not the fact that he's got to design these millimeter wave integrated circuits. It's not the fact that he's got to, put the antennas near his integrated circuits to be able to get the signal out. His biggest problem is thermal. So it is a serious issue. Of course, not everyone's using gallium nitride in their phased arrays for 5G. Of course, that's silicon or silicon germanium. But still, the point still remains that even there is often a heat problem that needs to be addressed. And this person is not using gallium nitride, and they said their biggest problem was heat. Packaging challenge in number 3 is beamforming trends, and I don't have a whole lot of time to stay on this slide, just to say that there are multiple ways to do the beamforming. You may remember from this earlier slide, let me go back to it, that there's this manifold, this power divider network. That's also called a beamforming network. That technology can be implemented multiple ways. You can have a single analog beamformers, multiple analog beamformers. I just finished an array where we have a multiple, for a customer, where we have a multiple beam analog beamformer. You can have multiple beam digital beamformers, or you can do optical beamforming. There are multiple ways to do it. And you have to make a choice there. And guess what? Every single one of those have packaging interconnects. So you're either going to be dealing with analog microwave and millimeter wave signals with single and multiple analog beamformers, or you're going to, if you do digital beamformers, you're going to be dealing with data bandwidths that are hundreds of gigabits per second coming out of your phased array, and that's also a challenge, right? Where you've got to move around these extremely high data rate signals. So signal integrity on those lines becomes absolutely critical. Or if you use an optical beamformer, now you've got to deal with the optical packaging issues, getting those optical signals in and maintaining the precision of the connectors that are required for optical systems. Again, challenges, but opportunities for packaging engineers. These are some details here where I've described a little more about the various ways that you can use to realize the beamforming, the power divider network, and other architecture changes here on these slides. And then now the last challenge, the fourth of the challenges, is the integrated circuits that are used. In the early days of phased arrays, the integrated circuits that were used were mostly gallium arsenide integrated circuits. They're face-up die that were wire bonded, and there was at the time everyone thought that this packaging density for this module here on the top left was very, very high, but it turns out it really wasn't. And the functionality for the integrated circuits was divided amongst multiple ICs. And then as time and technology, as time went along and technology improved, another approach came along for phased arrays called tile modules, and the functionality reduced to just a couple of ICs, but they were mostly military applications for those. And then the technology matured even further to now having phased array integrated circuits in one IC. There are multiple companies now selling phased array integrated circuits that are single chip ICs fabricated in either silicon or silicon germanium. And then the next level of integration and maturity is that now multiple TR functions are integrated into a single wafer. So you have now wafer level phased arrays. So now you don't have individual modules. Instead, you have multiple phased array functionality into a single wafer. And Gabriel Rabiz over at UC San Diego has been doing obviously a bunch of work in that area for quite a while now. And so you get increasing levels of integration, but increasing levels of packaging challenges. As you increase your density and increase your IC functionality, you also inherit packaging problems you didn't previously have. So what are the solutions for some of these? Some of the solutions, that's how I'm going to end this talk, is discuss a few of the solutions. One of the solutions is to have these integrated circuits that have multiple phased array functions integrated into one integrated circuit. For instance, shown here is a chip that has several and one chip feeds several antenna elements, and this actually is a 64 element dual polarized antenna, and it's also out of UC San Diego, Gabriel Rubiz's team there, and this antenna design has some pretty significant packaging challenges. Obviously, you've got the challenges of how do you get the signal? How do you get where am I at? There we go. How do you get the signal from the antenna element to through the circuit board and into this IC? How do you do that? How do you then get the signal from these integrated circuits and power combine them together so that you can come out in this nice little spigot here, right? There's the vertical polarization and the horizontal polarization here. For those who are in the communications area for mobile phones, this maybe will be minus 45 and plus 45 might be an analogy for what you're used to seeing. And then how do you get the heat out of this? There isn't a heat path on the backside of this board. On the backside of this board are antenna elements. So you can't take the heat out of the backside of this board. But you can't land a piece of metal on top of this board to pull out the heat because you have transmission lines there. So how do you get the heat out, right? You've got to take the heat out the sides of the board. The sides of the board or some other method. But anyways, this is a technique that people are using. Another technique that people are using is heterogeneous integration, where you're able to integrate multiple ICs into a single package along with antennas. Here's an example here in the top right, where you've got thermal vias for your IC. Maybe this is a silicon IC, and then a MMIC, maybe gallium arsenide or gallium nitride. And you have a heat sink on the bottom to pull out the heat, vias here to take the heat out of the ICs. And then you transition through the circuit board out to some radiating antenna element. And other approaches, but all kind of the same thing. You've got integrated circuits you've got to get signals into, and you've got to get signals out of those integrated circuits into antennas that radiate energy, and you need to make those transitions happen as close to the chip and the antenna as possible. There are also the chiplet approach, right? And the monolithic approach, where everything is integrated onto a silicon substrate, and you have now this things that are bonded. So you have this mixed material solution at the wafer level. So this is a very popular method. There's a lot of research going into these heterogeneous integration methods to solve these packaging challenges. And so conclusions, there's let's see, there's 4 challenges we talked about, which is packaging density, and that's due to the spacing between antenna elements in the array, heat transfer and dissipation. In the extreme example of that gallium nitride IC, you saw that the heat density was equal to or more than the heat density coming out of a clothes iron. And beamformer technology also impacts the packaging, and integrated circuit trends are impacted by how well the electronic packaging is done. So if you plan on developing phased arrays, you'll need to address these challenges and many others. This is just 4 of the challenges that exist.
Awesome. Thank you, Rick. Great presentation. Again, if anyone has a question, please send it through on the chat box. One question came in, I believe it was on slide 17. You referenced APAA, an acronym, and I guess they were wondering what that stands for. And also, are the 2 figures that you show here, is one the front side, one the back side of the device?
Yes, yeah, and you broke up a little bit. What's the acronym that they were asking about?
Oh, sorry about that. APAA.
Oh, yeah. Where is that? Which slide is that? Yeah. Where is that? Yeah, I don't remember which slide that is on, but it doesn't really matter. So an APAA is an active phased array antenna, is often how that acronym is given. The military acronym is AESA, Active Electronically Scanned Array. The APAA is more of a commercial acronym for phased arrays.
All right. And again, this slide that you have up now, is that the front side and the back side of a unit?
Correct. Yep. That's the back side and the front side of the same board. That's right.
All righty. And I guess a question I have you seen any data out there, obviously on the larger array systems? There's a lot of trade-off in terms of liquid cooling versus air cooling, and size-wise, in case you're going to size the arrays bigger if you don't want to go down one road versus the other. So have you seen any talks on where that break point is in terms of thermal to transition from one to the other? Or?
Yeah, so the heat dissipation is a big item, and for receive-only antennas, it's less of an item. But for where you're doing transmit and receive out of the same item, or you have a transmit-only antenna, the transmit sections can dissipate significant heat. And but there are ways to do it without liquid cooling. but the cutoff in the amount of power per element in an array where you could use liquid or air cooling versus liquid cooling, in my experience, is generally in the single digit watts per element in the array. And that goes down as you increase operating frequency. So as you increase operating frequency from a couple of gigahertz, up into the millimeter wave, 28, 30 gigahertz, that drops significantly. So it's the amount of power you can have in each element and not have to use liquid cooling drops inversely proportional to frequency.
Ready? Another question that came through: with high heat flux and the use of optical beamformers, does this add significant complexity requiring matching materials given the presence of higher temperatures that must be used to prevent temperature-driven movement of the optical devices?
Yeah, there you go. That's a big deal. In fact, we were just doing a product design that has some photodiodes in it, and other optical components in it, and it's very sensitive to heat in the processing temperatures, because things move around. You can't afford things to move around much when you have an optical components. So yes, heat dissipation and optics combined, and more to the point, varying levels of heat load. So you have to go from a heat load where the ray is off to a heat load where the ray is fully on and transmitting power near continuous duty cycle, near 100% duty cycle. You go from something very cold to very hot, and optics, optical components just don't like that. Optical components like to fail when that happens. So it is a challenge. That is a good question, and absolutely correct. There is another opportunity for electronic packaging engineers relative to phased arrays. How do you solve the optical interconnect and optical beamforming challenge with high power phased arrays? It's not easy.
Definitely. Another question that came through: what limits the number of devices a given phased array can communicate with?
Okay, yeah. So the number of users that a given phased array can communicate with at one time. So that's a really interesting question. So let's say you've got 2 users and you've got one beam. You can point a beam at one user and just communicate with that one, ignore the other. You could do time domain like Wi-Fi does and do time domain multiplexing. But what is proposed and is being implemented in these 5G systems is to have multiple beams that communicate with multiple users. My fingers represent antenna beams, right? And so you have multiple antenna beams communicating with multiple users at the same time. So this beam is dedicated to a particular user or group of users here. So in that case, what limits the number of beams you can have, if you have, this is an important distinction. For an analog beamformer, the number of beams that you can have, simultaneous beams, is equal to the number of analog beamformers that you have. And for most systems, that's limited at 3. If you have digital beamforming, you can have multiple simultaneous beams, and there's theoretically no limit to the number of multiple simultaneous beams you can have with digital beamforming. But the price you pay is the high data bandwidth that exists with these digital beamformers in the gigabit per second, right, range. And it's not easy to do handle all that data. Once you get the data out of the array, so let's say you do a great packaging job, you get all that data out. Now you got to do something with the data, and that's yet another problem, right? What computer are you going to use to process all that data? So, anyways.
Good deal. All right, just checking on any other questions coming through on the chat box. Let's see. So, comment that came through: liquid immersion is a solution in use for servers and AI systems, but addition of optical elements suggests that this will be impractical with optical beamformers.
Yeah, that's an interesting comment. I've not seen liquid immersion used in phased arrays. I've seen some research. In fact, I performed some early research on using spray cooling on phased array components, but I've not seen liquid immersion.
All right.
Not that it couldn't be done. I just haven't seen it.
Another one that came through, it's called an AIO antenna in package. Any comment how this technology works?
Oh, I see that. I see that question from Tom. Yeah, so it's they're using liquid crystal polymer technology in an AIO antenna. I'm familiar, of course, with liquid crystal polymer solutions, and they're wonderful, right? Liquid crystal polymer has its uses. It has its limitations, but also has uses, and some depends on the formulations you use for it. But I'm not familiar with the AIO antenna in package methodology that Tom is bringing up. I'm not familiar with that.
Okay. And Tom was also commenting that Fujikura Pascom is out with some millimeter wave using LTP technology.
Yeah. It's called the AIO. Thanks, Tom. I'm going to look into that.
Yeah. All righty. Not seeing any other questions coming through on the chat box. Thank you, Rick, because it's a great talk. Definitely informative and definitely a great overview of the radar technology.
Thanks, Harvey.
I'm going to pass it back over to you, Dave, I think, for closing.
Dave, you're muted still.
Second time. Oh, where'd my, come on. So I'm a little behind here, but I'll get there. Good. All right. So I think we certainly thank our presenters, our 4 presenters today. This was excellent. And thank you to Tom Terlizzi and Chandra for putting together this session way back in ancient days prior to January, when we were anticipating that the symposium would be held on May 7th. So thanks to all 4 of our presenters. What you've seen here today is the second of our virtual sessions that we've extracted from what would have been the Symposium 2020, Symposium 47 program. If you enjoyed this and find it worthwhile and have not participated in a previous IMAPS New England chapter session, please check our website, add our schedule for the next virtual events. Anyone who's registered for this event is likely going to find that will result in at least 1 email in the future from the IMAPS New England chapter. I think that's a reasonable statement. All of the questions are appreciated. We appreciate the participation of everyone. Our next event is going to be a bit unusual. It will actually be a presentation that I will give. It will be in place of our normal annual holiday meeting that we have in December. On December 15 at 5 o'clock, we're going to do a virtual presentation. I'm a member of the Boston Main Railroad Historical Society. I'm a lifelong railroad buff. I developed and gave a presentation a couple of years ago up in Plymouth, New Hampshire for a B&M Society meeting. And we had a packed house, great turnout. It was wonderful. My subject was the development of snow trains. This started in January 1931 by the Boston Main Railroad. It was essentially a marketing ploy in the depths of the first couple of years of the Depression, Great Depression, to find a way to put commuter equipment to work and to put crews that were idled on weekends to work. And it was termed a snow train. The first train ran in January 1931 from Boston North Station to Warner, New Hampshire. You probably don't know that there used to be a railroad line that ran to Warner, New Hampshire. You can't find any evidence of it today, really. The town of Warner just celebrated the 75th anniversary last year and held a celebration event, which I went to. And in fact, the dinner that we were served was exactly the same menu that was served to all the passengers on that very first snow train in January 1931. It's a very interesting story. I hope you might find this enjoyable. Consider attending and listening and watching. I have a number of photographs. I have examples of schedules and so on to give you an idea. That first snow train event spread like lightning across New England, New York State, and across the country into Quebec. It was a concept that really gained steam. And if you think about 1931, not many people in this country had automobiles, and not many people either knew about skiing or had any idea what it really was. And this concept of snow trains running to different destinations really had an impact on the development of what has become our skiing industry in this country and North America. It's actually quite a fun story. The way I think of it is, if you were single and say 28 years old and living in Boston in 1931, you could walk over to North Station on a Friday night and take a train to a small town in New England. And for let's say a relatively modest fee, you could have a weekend event. Maybe you only did it once a winter in the Depression, because that's all you could afford. But it was a way to get out and enjoy, and in fact, meet other people. And since I've given this presentation, I've given it a second time because I was asked to. And I have had people come up to me and say, my grandparents met on a Boston and Maine Railroad snow train in 1935. Well, that's why those people are here on the planet. Anyway, it's a little bit of fun. We'll have it posted on our website. After December, we are planning to hold a chapter technical meeting in January. Richard Holman is handling the organization of that chapter meeting, and that will be posted on our website. Then we will have another of these virtual symposium technical sessions in February. We haven't chosen a date yet, but it will be the second RF and microwave presentation session that we had planned for the 2020 symposium. So you will find these items being added to our website. It's the IMAPS New England website, www.imapsne.org. And we certainly hope that you have found all of this useful and will plan to attend our future events. With that, I think we will close. Matt, anything else?
I think you covered it all, Dave. Thanks. Just want to thank everybody for joining in and thank all our speakers and our session chairs. That was excellent. Thanks very much. Have a good weekend, everybody, and take care.
And we're finishing 10 minutes early. All right. Thanks. Thanks, everyone.
Thanks, guys. Bye.
Bye.
Bye.